Part A. Total cost to drill to a depth of 500 meters. In Part A, we need to calculate the total cost to drill to a depth of 500 meters. Here's the setup. The cost of drilling the first 50 meters is $500, and the cost to drill each additional 50 meters increases. This forms an arithmetic sequence. Next, let's find out how much the cost increases by for each 50 meters drilled, or in other words, the common difference. The first term, U1, or the cost of the first 50 meters, is $500. The second term, U2, or the cost of drilling from 50 to 100 meters, is $640. Thus, to find the common difference D, we use the formula D equal U2 minus U1. D equals to 640 minus 500 equals to 140. So the cost of drilling increases by $140 for every additional 50 meters. To reach 500 meters, we need to drill 10 segments of 50 meters each, or just simply divide 500 by 50, which gives us 10. Thus, the number of terms n is 10. Now we'll use the sum of formula for an arithmetic sequence to find the total cost. Substituting our values, we get: first, calculate inside the parentheses. 2 times 500 equals to 1000, and 10 minus 1 times 140 equals to 1260. So we have. Therefore, the total cost to drill to a depth of 500 meters is $11 and $300. Maximum depth that can be drilled with a budget of $76,000.
Next one in the Part B, maximum depth that can be drilled with a budget of $76,000. In the Part B, we're given a total budget of $76,000 and we need to find the maximum depth that can be drilled without exceeding this amount. Each 50-meter segment forms a term in is a arithmetic sequence where the first term or the U1 is $500. The common difference or the D is 140, which we found in Part A. Next, we will use the sum formula again, but this time we need to find the maximum number of terms or 50-meter segments. The total cost under or equal to $76,000. Let's set up the inequality. So the Sn is equal to 76,000. Substituting in the sum formula, we get. Substituting A equal to 500 and D equal to 140, we have. Simplifying inside the parentheses, which becomes. Next, we will multiply both sides by 2 to clear the fraction. Expanding the brackets and moving 152,000 to the left side, we get. So this is a quadratic inequality. We can solve it using the quadratic formula, where A equal to 140 and B equal to 860 and C is equal to minus 142,000.
Now, let's substitute these values. Then, inputting it all in the calculator will give us, and simplifying further, and finally solving the square root, which will give us two possible values for n equals 30.3 or n equals minus 37.2. Since we can only have a positive number of terms, we use n equals 30.3 as our answer. And we will also run it down to n equals 30 because we cannot go over our budget and the number of terms may not be a decimal value. Now, let's find the maximum depth. Each term represents a 50-meter segment. So, to find the maximum depth, we multiply the n by 50. So that makes 30 times 50 equals 1,500 meters. Therefore, the maximum depth that can be drilled within the $76,000 budget is 1,500 meters. So, to summarize, this problem shows how sequences can be used to calculate real-world costs over time, especially when expenses increase steadily. In Part A, we calculate the total cost to drill to 500 meters with the sum formula for our arithmetic sequence. Then, in Part B, we use the sum formula again and the quadratic formula as well to find the maximum depth that could be drilled within a $76,000 budget. By applying sequences and series, we can break down complex expenses into manageable steps and make predictions within a budget. Thank you for watching, and we hope this explanation will help you understand the way to solve questions or problems like this. Good luck.